Well, we have covered quite a bit of material, and we were in the middle of talking about other property relations, the volume expansivity, isothermal compressibility, isentropic compressibility, velocity of sound, and Joule-Thomson coefficient. We'll get to these. So here are some of those properties. So a new property known as the volumetric expansivity is defined in terms of the specific volume and how the specific volume changes with respect to temperature holding pressure constant. Okay? Or the isothermal compressibility is -1 over the specific volume. The rate of change is specific volume with respect to pressure holding the temperature constant. So if pressure goes up, typically the specific volume decreases at constant temperature. And then isentropic compressibility. How does the volume change with pressure as entropy is constant? Here is the velocity of sound. It's related to how the pressure changes with respect to specific volume, constant entropy, and then the specific volume squared and the square root. And then the last is the Joule-Thomson coefficient. We'll spend some time talking about that. So how does the temperature change as the pressure changes holding enthalpy constant? Here's a problem. Let's go ahead and solve it. So we have a mass of copper, 2.2 kilograms. It's a sphere. It's allowed to change by more than 0.05% if the pressure on the sphere is increased from 10 bar while the temperature remains constant at 300 Kelvin, then determine the maximum allowable pressure. So we want to find the final pressure P2, the maximum allowable, knowing that as we increase the pressure, the volume is going to decrease. There'll be some isothermal compressibility for this, even a solid like sphere. And so this piece of information is we want the volume to change by no more than 0.05%. So the final volume compared to the initial volume, first of all, that's going to be a negative quantity, right? The final volume minus the initial volume will be negative. So we'll put a negative in front of that to make it a positive volume change. And we normalize it by the initial volume. And we want that to be less than or equal to 0.05%, which is equal to 0.0005, turning it into a fraction. From percentage into a fraction. Okay, we're given some properties for the copper. We're given the mass density, beta, which is not what we need right here. We need kappa, the isothermal compressibility. What was kappa defined as? It's -1 over the specific volume times the rate of change of specific volume with respect to temperature holding pressure constant. No, I wrote that wrong. With respect to pressure holding temperature constant. There you go. True? Let's just jump back and take a look at K, or kappa, isothermal compressibility. How the volume changes with respect to pressure holding temperature constant. Now, can we turn this specific volume into a total volume? A rate of change of total volume with respect to pressure holding temperature constant. For a fixed amount of mass, we can. So you go from specific volume to total volume, V. And then you approximate this derivative by V2 minus V1 divided by P2 minus P1. So we've approximated that derivative. And then you have 1 over V1. So I put the negative sign right there in front of the V2 over V1. Okay, so if we want to do this, we can unravel this. We have the final pressure minus the initial pressure is equal to minus V2 minus V1 divided by V1, 1 over kappa. Did I do the algebra correct so far? Do you follow that? Okay. And so if you want to find the final pressure, then there you go. The final pressure is going to be greater than P1 by that amount. Substituting numbers, so we start at 10 bar, and we have this minus V2 over V1. Well, that's our limit. We don't want the volume to change by more than 0.05%. And then we divide by the parameter for the isothermal compressibility, which is 0.776 times 10 to the minus 11 meters squared per Newton. We notice this is in bar, this is in newtons per meter squared, so we'll use a unit conversion that a bar is 10 to the 5th newtons per meter squared. True? So the newtons go, the meters squared go, we're left with bar. And so what we find is that P2 is equal to 654 bar. If the final pressure is greater than that, then there will be more than 0.05% volume change. If it's less, it'll be less than that volume change. Let's look at part B. What is the final volume of the sphere in cubic centimeters? Well, so I'll just kind of tuck it in over here. The volume is equal to, and it's the final volume that we're interested in, is equal to the mass divided by the density, or if you want to do it this way, the final volume is 0.9995 times the initial volume. We're going to assume that this initial density is applicable for the initial case without a high pressure on the sphere. And then 0.9995 times volume initially is the mass divided by the mass density. True? So our final volume is 0.9995. How close is that to 1? It's close enough to 1. Even though the volume changed by 0.05%, the difference is far out there, beyond 3 significant digits, but there you go. Let's do the math. 2.2 kilograms, 888 kilograms per meter cubed, and then you want to convert 100 centimeters is equal to a meter, true? And then cube that. So it's 10 to the 6 centimeter cubed per meter cubed. And you calculate then the volume to be 2,476 centimeters cubed. Good to 4 digits. Really should round that off to 80. Close enough. Any comments or questions? Look good? Look doable? I think if you look at past exams, I had this problem on a previous exam. You remember it, John? Last semester. Let's move to the Joule-Thomson Coefficient. This is just a parameter or a property defined in terms of others. So the Joule-Thomson Coefficient relates how does the temperature change as the pressure changes for an isenthalpic constant entropy process. It's very applicable for flow through a throttling device. And so as the flow moves from left to right in a well-insulated device so that there's no heat transfer, there's no shaft work, you do a little control volume analysis around it, true? And if you neglect changes in kinetic and changes in potential energy, then you find that H1 is equal to H2, true? Isenthalpic. But the pressure has significantly changed through the throttling device. The pressure at 1, how is it related to the pressure at 2? Which one's greater? Is the pressure at 1 greater than pressure at 2? Always. Right? Always. And then you say to yourself, what about the temperature at 1 and the temperature 2? Is it greater? Is it equal to? Is it less? Which one is it? And it really depends on the Joule-Thomson coefficient. Okay. As a background, if this was a flowing, if it was a true ideal gas flowing through the system, can you tell me what is T1 compared to T2? Or think about, what is T2? Is T2 lower than T1, equal to T1, or greater than T1 if it's a true ideal gas? It's isentropic. And for a true ideal gas, H is a function of temperature only. So it is equal. It's equal for a true ideal gas. For real substances, it's typically often less. T2 is often less. You're coming from understanding or studying refrigeration, true? When you had a pressure drop through that expansion valve, the temperature dropped in refrigeration applications. So that's what you anticipate. But what we can do is approximate this derivative as the final temperature or outlet temperature minus the initial inlet temperature, pressure, like that. Is that a good approximation of that derivative, assuming constant H? Yes, or applicable to constant H. And such that I can solve to find that T2 is equal to T1 minus mu sub J times P1 minus P2. Did I do the math right? Did we do it okay? Why did we write it like this? Why did we write P1 minus P2? Because P1 is always greater than P2, isn't it? To force the flow through the throttle, it's not going to happen any other way. P1 is always greater than P2. All right, so this is positive. And so if the Joule-Thomson coefficient is positive, then this is positive, but you subtract it from T. So T2 is going to be less. T2 is going to be lower than T1. So if the Joule-Thomson coefficient is positive, then T2 is less than T1, true? But for some substances under certain circumstances, the property known as the Joule-Thomson coefficient is negative. When the Joule-Thomson coefficient is negative, then it's hot when it comes out. It's warmer when it comes out. Okay? Because if this now is negative right here, then it's a negative of negative, that's a positive. So T2 is greater. Okay? If mu sub J is equal to 0, T2 is equal to T1, and that's for the case of an ideal gas. True? Yes, sir.
Is the sign change for those P's necessary?
Well, I wanted to keep P1 greater than P2. Otherwise, I've got another negative always that I've got to keep track of. Does that make sense?
Yeah.
So I needed P2. I needed this subscript to match that subscript in this derivative when I approximate it with a difference ratio of differences, right?
Yeah.
Does that make sense?
Yeah.
Okay. Here's a plot. I grabbed it off of Wikipedia, and it's for the substance nitrogen. Okay. So it's looking at a temperature, entropy diagram for nitrogen. Look at the values of the entropy. They don't make much sense. 3, 4, 5, 6. Physically, I don't relate to those, okay? But look at the values of temperature. 100 Kelvin, 300 Kelvin. I can relate to those. This is around atmospheric temperature, 300 Kelvin. This is super cold, 100 Kelvin, cryogenic temperatures, okay? Okay. Now, they show a red line right in here. What does that look like? Can you interpret that red line? What does that red line show us? The dome. Underneath that, what do we have? Two-phase mixtures. So at the top of the dome, what do we have? Critical point. So nitrogen does have a critical point, and it's about this temperature, and that's the entropy for the critical point. So you can look up and compare. About ready to go?
Yeah. If anyone has any design projects to turn in, you came in late, give them to me now.
Yeah, please turn them in now, okay? So this sequence of states going off to the left of the critical point is all saturated liquid, true? And this is all, I'm sorry, saturated vapor. And this is all saturated liquid, true? Okay, what do we call this region above the critical point? Supercritical. Supercritical. The substance nitrogen is a supercritical region. Now, what do we call when it's over in this region? Okay, it's like an ideal gas. Nitrogen almost always behaves as an ideal gas. So way up in here, it behaves like an ideal gas. Okay, now let's do this. Let's do this. If somebody says, I want you to show me on a temperature entropy diagram a line of constant entropy and then a line of constant temperature, that's really easy, true? A line of constant entropy would be something like, here's all the values of 6 kilojoules per kilogram Kelvin, a line of constant entropy. Here's a line of constant temperature at 200 Kelvin. It's all just horizontal. Those are easy. But they also plot lines of constant temperature, pressure. Can you see the lines of constant pressure? So up here they put the pressure labels, 1 bar, 2 bar, 5 bar, all the way to 100 bar. And so let's follow this black line down. This line right here is 1 bar. It comes down, down, down. And then it goes into the two-phase region all the way across. Boom, there you go. 1 bar is around 1 atm. If I have liquid nitrogen and it's in a container and I have it open to the atmosphere, what will the equilibrium temperature of that nitrogen be in that container, that liquid nitrogen? Around 77 Kelvin. It would be very, very cold. And that's what they're showing right around here. It's around 77 Kelvin. That's the boiling point of nitrogen, cryogenic. Used to, if you had something on your skin and you needed it cut off, I know you're all too young for this, right? You have healthy skin and all that, but when you get older, you get blemishes. And you would go to the doctor and you stick a Q-tip into a liquid nitrogen jar. The doctors always have it. Bring it out, rub it right there. What does it do? Instantly kills it all. Then he could take a scalpel and take off your blemish. True? I've had it done, and you will too, probably. So, but now, guess what they do? They just take a little can, and they go like this. Psh. Come on now. How many people have gone to dermatologists? You know what I'm talking about. So I went there and I said, what about this? He said, you want it off? I said, yes. Out comes the can. It used to be a little Q-tip with liquid nitrogen and dab it on there. Now it's just a little psh, and it's frozen. Okay? All right. So now what about this pressure right here? This is 200. Can you trace this line of 200? 200, that's a high pressure and it goes down like that. True? Okay, so we're getting acquainted with lines of constant pressure on this TS diagram. Where are lines of constant enthalpy, constant H, on this TS diagram? There are the blue lines. You have to look really closely. Let me erase some of this down in here. But what do they give us for the units on this blue right here? That's 50 kilojoules per kilogram. And then 100, then 150, 200, 250, 300, 350, 400. Here's one at 430. So if we trace the line of constant enthalpy at 430, it looks like this. And that's a line of constant enthalpy, where the enthalpy value is 400 and 30. Let's trace a line of constant enthalpy of 150. It's right here. Goes up and down. So those are the lines of constant enthalpy, okay, on our TS diagram. Now, where in this whole plot is the enthalpy a function of temperature only? Where in this plot is enthalpy only a function of temperature? Far to the right. That's exactly right. And so what happens is you see that this line of constant enthalpy of 350 is flat. And then it starts to move. But out here where it's flat, what does a line of constant temperature look like? Flat. So anywhere along this line, even though entropy is changing, even though pressure is changing, the value of temperature is the same and the value of enthalpy is the same. But if I boost the temperature, if I go from 200 to 250, now the enthalpy is different. But this is the region where enthalpy is only a function of temperature. In what region is enthalpy a function of temperature and pressure? Everywhere else. True? Everywhere else. So basically in this whole region, it's a function of temperature and pressure. Now down in this region, somebody says enthalpy is changing, but the pressure is constant. Well, that's because temperature and pressure are not independent in the dome, are they? They're not independent. So you would have to think of maybe in the dome, the enthalpy is a function of temperature and quality, or pressure and quality. All right. Now let's consider throttling process, where you're going from, let's say, 200 bar to 100 or 1 bar. That's a throttling process, going from high pressure, low pressure. Let's start with the state A. So it's at 200 bar, and it's around 300 Kelvin, true? You then put it through a throttling device, and it drops the pressure to 1 bar. It's flowing through that throttling device. What is the temperature that it comes out of that throttling device? Well, it comes out at this state, B. And so we can read off the temperature at B. It looks like it comes out around 270. So through that throttling device with the nitrogen, it's a real gas. It's up in that supercritical region. It always stays a gas. It's not an ideal gas, although state B is very, very close to being an ideal gas. But state A definitely is not. And you see that the temperature dropped. So the Joule-Thomson coefficient along that path, almost anywhere along that path, it was a stronger positive, not so strong a positive value. But then finally, the Joule-Thomson coefficient out in here goes to 0. All right, let's consider a point C. What's the pressure at C? 200. Same pressure as A. But what's the temperature at C? Wow, that's really cold. That's 130 something, 133 Kelvin or something like that. True? At point C. If you let it reduce the pressure to 1 bar, isenthalpic process, where is the outlet of that throttling device? Where is it at? Point D. True? So the 150 is a line of constant enthalpy. True? It stayed on that line. So it came out at 77 Kelvin. It came out in the two-phase region. Visually, can you interpret or visually estimate the quality X at state D? What is visually your estimate of X of D? 60%? Okay. Anybody else have a different value? How about if D was way over here? What would be the quality at this point? About 5%? 0.05? What happens if it's right here? About 95%. And so if it's right there, it looks like it's around 60%, right? 60%. Meaning, how much of it is in the liquid state? How much of it's in the vapor state? If it's 60% quality, 40% is liquid, and 60% by mass or by volume? By mass, okay? By mass is in the 40% still ready to boil. So it's in liquid state. So here it is. Can you tell that the Joule-Thomson coefficient is it's not as large there, but it's very steep right here. So right in this region, you have a very large Joule-Thomson coefficient, a large positive Joule-Thomson coefficient, and then it's still pretty strong there, but not as strong. Where could we get the case where we go through a throttling device and the temperature of nitrogen goes up? Keep going to the left. Keep going to the left. So let's say we want to start at a pressure of 1,000, true, and we'll start at 250. So this looks like the intersection of 250 with the 1,000, right? Maybe I should have picked that one right there. A little over 1,000, okay? And then if you drop the pressure, it's going to stay on a line of constant enthalpy. And anywhere starting here and maybe ending here, what's the temperature do? It goes up. So we have a negative Joule-Thomson coefficient in that region. Okay. You can see the sequence of points to the left is one behavior of the nitrogen, and to the right is the other behavior of the nitrogen, right? Okay. Well, you can go to different websites and see statements about the Joule-Thomson effect. Here's just American Gas Association. I just picked it for random. And they have a glossary, and they define terms. So I said, oh, what do they say about the Joule-Thomson effect? The cooling, which occurs when a compressed gas is allowed to expand in such a way that no external work is done. Not only is there no external work, there's no heat transfer. True? Isenthalpic. It's an isenthalpic process. No heat transfer. Adiabatic. All right. And then they also say the effect is approximately 7 degrees Fahrenheit per 100 psi for natural gas. Well, they're interested in natural gas, right? So if you have a pipeline of natural gas and then you have a valve in it, which they all do, to regulate the flow, to turn it down, whatever, to limit it, turn it off, and you have maybe, it's easy to have 1,000 psi right here, 1,000 psi, no problem, and it's 70 degrees F. Is that intuitive to you? You put your hand on it, it's nice, calm, not very hot day, the natural gas is flowing, 70 degrees F in this pipeline, and they drop it to 100 psi across that valve. If this is true, what's the temperature? Right here. 0. 0 degrees F. Is that cold? Yeah. Well, if you have just a little bit of water in there, what's going to happen? It's going to freeze. You'll get hydrates, you'll get solids, it'll freeze. And it could, if it flows through and some of the water deposits, then more water flows through, deposits. Just a little bit of water in natural gas could build up and plug it. Then you have a real problem. Then not only do you have to sort of shut it all down and then come in here and warm it up to get it to melt, get rid of it, but you'll probably have to get it much higher than just 32F to get rid of it. So they have, in any natural gas pipeline, they have severe restrictions on the maximum amount of water that can be put into it from different wells. So if you have a well here, well there, It's coming out of the ground is moist, you have water in it, you've got to get rid of that water. Otherwise, the pipeline companies will cut you off and won't let you supply into it. Okay, it's a real problem. And I forget the limit, it's like 7 pounds per 1,000 something cubic feet. I should know that number, but I don't. Is the maximum water content. And so that's a real concern. Let's move now to enthalpy departure chart. It's just like the compressibility chart. So if I'm interested in calculating H2 minus H1 for real gases, not ideal gases. What I'll do is I'll approximate it assuming that it's truly a function of temperature only, neglecting the effects of pressure. And that's when they put this asterisk up here. This is a true ideal gas. And it's only a function of temperature. The final temperature T2 and the final initial temperature T1. And then we'll have some correction or departure, depending what text you read and what parts of the text you'll read. But this is an enthalpy correction or enthalpy departure from the ideal gas behavior. So that best estimate of our enthalpy accounting for pressure minus the ideal gas value of the enthalpy, where these temperatures are the same. T2 is the same. All right. And then you also have the correction accounting for the P1. So H minus H star. And if you just look at the math, this and that are the only surviving terms, so the right-hand side is equal to the left-hand side in this equation. Well, these enthalpy departures are not trivial, but they do the derivation to come up with it. But you can see it's the rate of change of compressibility factor with respect to the reduced temperature, blah, 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 integrated with respect to the reduced pressure, blah, blah, blah. Don't worry, no homework problems where you have to do the integral, but they've tabulated this in a chart. And so the chart, what we'll do is spend a little time looking at right now. So I have to scroll down. When you're introduced to a chart, I recommend you look and see what is on the x-axis and what is on the y-axis. So the reduced pressure, what is P sub R? Is it the actual pressure divided by the critical pressure for our substance? Sure. And you can look it up, argon, nitrogen, methane, whatever gas you're interested in, you can get that critical pressure. Also, on the y-axis, what's that? Well, that's our enthalpy departure or correction from the actual best estimate to the ideal gas, considering temperature only. They normalize it by R bar T critical. Okay, so what you're going to do is you're typically going to come in and try to read off this chart and read over and pick off a value and use that value. Oh, it's 2.5, something like that. Well, here are lines of constant TR. That's the actual temperature divided by the critical temperature. So this Y is read by first coming in with the PR. Maybe the PR is 2 as an example. And the TR is 1.4. You would find where they intersect and you would read off that value. Maybe it's 1.2. Doesn't that look like about 1.2? And that's how you use the chart. Go back to the equation and unravel it to get a better estimate of the enthalpy change. That would be maybe for state 1. And then maybe state 2 is, I don't know, maybe it's 1 here. And 1.3 right there is 1.3. So that I'd read off, and it would be, I don't know, 0.65. It's a little bit of an art. Good luck getting 2 significant digits, right? Reading the chart. So, but this is very old school. This is pre-computers. They did a lot of this work, well, maybe not pre-computer, but early computer, early supercomputer. This is a problem. What you would do for this problem is you would want to find the critical temperature and the critical pressure for argon, that gas. When you look it up, you find the critical temperature is 151 Kelvin. The critical pressure is 48.6 bar. And then for state 1, you want PR, whoops, let me put it in parallel here, TR1 and PR1. So state 1, this is state 1 coming into the turbine. So it's 325 Kelvin, you divide it by 151, and you get 2.15. And then pressure divided by the critical pressure, you get 2.06. You flame off to the chart looking at that value of TR and PR, and you get, maybe I should draw it like this, you got that the correction factor H bar asterisk minus H bar divided by R bar TC is around 0.4. Error, that's where you're really going to get your big error right there, reading that chart. And then the same for TR2 and PR2. So you get TR2 of 1.56, PR2 0.82, and you read the chart and you get H asterisk minus H bar divided by R bar TC is equal to about 0.38. So then you have the equation so that the power per unit mass out of the turbine is the inlet enthalpy minus the exit enthalpy, true? Since we like to work H2 minus H1, just put a minus sign in front of that H2 minus H1. The equation is very much similar then. Minus H2 asterisk minus H1 asterisk, true? And then continuing that equation, it's going to be minus H asterisk minus H bar divided by R bar TC at state 2, R bar TC, this is plus minus H asterisk bar 1 minus H bar 1 divided by R bar TC, R bar TC. Okay, I think I did that all correct, where this value of 0.38 goes in there, and the 38, and this value for this ratio is 0.40 at state 1. True? All right. If I want to calculate this, it's the specific heat times the temperature change, T2 minus T1. How do I get the specific heat for argon? It's going to be 5 halves R bar. That'll give me C sub P bar. I divide by their molar mass, and there you go. Does that make sense? You've seen how to do that, I think? All right. And then you have plus, and then you have this coefficient at the red. Then you have minus this coefficient, 41, multiplied by R bar, critical temperature, and if you want it on a unit mass basis, divide by the molar mass. And my calculations show that this entity right here, excuse me, is .8, and you subtract off 0.6, not much of a correction, to get a final answer of the work of the turbine produces 46.2 kilojoules per kilogram. Look reasonable? It's a little tedious, isn't it? You just use this equation right here, right? And so I need to unravel that equation. Okay. Let me do this. in the interest of time, let me just say computers exist. And how would you do this using some software that's pretty reputable? So if you go out and just type in mini REFPROP in the Google search, you'll come up with a link to the National Institute of Standards and Technology, U.S. federal government supported lab. In Boulder, Colorado, they have put out a program called REFPROP. And the REFPROP full version you have to pay a couple bucks for, a couple $100. But the mini version of it, that's why I put the mini in here, is any student can download it and have some access to some properties. So if you go to the mini REFPROP, you'll see where they say, hey, you're a poor student, we'll give it to you for water, CO2, R134A, nitrogen, methane, propane, hydrogen, and dodecane. And but don't call us if you have a problem. Support only available if you pay us money. But hey, you're a student and we understand. Go ahead and click and download and have fun. And it'll expire in every year it expires. So you have to go back and download. When it downloads, it typically puts it somewhere in the C drive in the program files folder, and you'll get a little folder called REFPROP Mini. Okay? And then with that REFPROP Mini, you're ready to run. One way to run is you'll just click right here and you'll start running the program. They give you a folder of those fluids and a folder of mixtures where there's one mixture if you are a student. Or you can also put this out onto your desktop. Well, here it is. I've started it up, and this is how it would look when you start it. You can see that you have file, edit, options, but go under units, and you can say, oh, I like to work in this temperature, Fahrenheit, degrees C, Kelvin. I like to work in bar, megapascal. I just noticed they allow us to work in ratio T over T critical, relative temperature for that substance. Okay. You can also just change it to CGS or MKS or English, PSI, degrees F, BTUs, all that. Let's put it Kelvin and bar. Okay. And then the substance. You want a pure substance? This is where you get your choice, carbon dioxide or methane or some other substance of interest, right? So you could click yes. And then you could then say, let's calculate at specified state points. So you just have to, I'm going to turn this around, type in some values. Let's say, I don't know, 300 Kelvin, 20 bar. True? And then maybe it went down to 250 Kelvin at 10 bar. And so it gives you the density, enthalpy, entropy. Let's say I was interested in knowing temperature 250 and the enthalpy of, I don't know, 700. It's like software should work, right? It should work for you instead of you work for it. So you're able to get properties coming in with any two independent intensive properties. And so then you can calculate. Also, you can plot, if you like, temperature entropy diagram. That'll let you change things, put lines of constant enthalpy, click OK, and then you can play. Okay. So you can see these are lines of constant enthalpy. It looks like it didn't extend them into that two-phase region, did they? They didn't do that. We can go back and replot temperature enthalpy, show in the two-phase region. So we can plot, and there it goes. They extended it into the two-phase region for those lines of constant enthalpy. There's more here than you can do. So I'll stop there since